Let's look at this function here. We want the second partial derivative of f with respect to x. So we start by getting the first partial derivative. When we do that, we treat y as a constant. So x cubed becomes 3x squared. If y is treated as a constant, we differentiate x squared here to get 2x, and then we just have the constant y squared tied to it. 2y cubed becomes 0 because it doesn't involve x. 2x becomes 2, and y becomes 0 because it doesn't involve x. Now we need to differentiate with respect to x again, so the 3x squared becomes 6x. If we differentiate this term here with respect to x, we just get the constant 2y squared. We are treating y as a constant. 2 goes to 0, of course. Here is an alternative notation for the second derivative of the function f with respect to x. So we've already actually got that second partial derivative. Here it is, 6x plus 2y squared. And we have to evaluate it at the point coordinates minus 1, 1. So we plug minus 1 in for x and plus 1 in for y. So we got 6x plus 2y squared. We plug minus 1 in for x. This should be a plus 1, but it doesn't matter because we're squaring it. So we get minus 4 for the answer. We can also consider examples of mixed derivatives. So here's a function of x and y, and we want to calculate this mixed derivative here. So what does this thing mean? Well, first of all, we have to get the partial derivative of f with respect to y. And when we've got that derivative, we differentiate it partially with respect to x. So we differentiate this with respect to y. That means we treat x as a constant, so x cubed will go to 0. In this term here, the 2x squared is a constant. So we differentiate y squared to get 2y. So 2y by 2x squared gives us 4x squared y. The next term is differentiated with respect to y to give 3y squared. Now we differentiate this thing with respect to x. So we treat y as a constant. So the 4x squared becomes 8x, and we have the constant y after it. We differentiate this with respect to x. Well, we get 0. Now what if we do the derivatives the other way around? In other words, what if we calculate this thing here? So we differentiate f with respect to x first of all. Well, let's do that. So we differentiate this with respect to x. Well, x cubed becomes 3x squared. When we differentiate this with respect to x, the y squared is treated as a constant, so we get 4xy squared. Now let's differentiate this with respect to y. Well, the 3x squared goes to 0. The 4x here is just a constant, so we have 4x by 2y, or 8xy. So notice that we get the same answer. So the second partial derivative of f doesn't depend on the order. So here's an alternative notation for this particular second partial derivative. So the subscript is yx here. So actually it's in reverse order in a sense here. So the first subscript indicates that the first derivative is taken with respect to y, and the second subscript x indicates that the second derivative is taken with respect to x. Of course, we don't have to worry too much about the order because these two will be the same for nearly all functions, well, all well-behaved functions. Let's take this example here. We want to differentiate this function partially with respect to x. Now we could differentiate it partially with respect to y first, but it doesn't matter. Okay, let's differentiate it partially with respect to x. So x cubed becomes 3x squared. The y squared is treated as a constant, so the 2x squared becomes 4x, so we get 4xy squared. Y cubed is treated as a constant, that goes to 0. Now we differentiate this thing with respect to the other variable, which is y. So if we differentiate this with respect to y, means the 3x squared will disappear. Y squared becomes 2y, so we get 8xy. Finally, we plug in x equals 1 and y equals 2.